Hello, I'm Chris Aber with the top 5 problems that we've encountered with clients' response plans over the years. And I've been doing this for over 40 years now. I've seen a number of hurricane response plans during that time, and most of them have at least one, if not all, of these problems associated with them because they were generated by people who weren't hurricane experts. And that's a problem when you're trying to generate or develop a hurricane response plan. Let's take a look at the top 5 here. Number 5 is the incorrect interpretation of that error cone. We've all seen that error cone around the track of the storm, and we interpret that as being that's an area where we're potentially threatened by the storm. But that's not really what the cone indicates. What we do is we take a look at the forecasts over the past 5 years and determine how frequently the center passed within each of these error circles. And in this case, Storm Geo, we use a 75 percentile error. So 75% of the time, the center of the storm track somewhere in these circles along track out to 7 days. We connect those circles with a tangent line and it becomes a cone. It says how accurate our forecasts have been over the last 5 seasons, but it doesn't tell how much uncertainty there is with the current forecast. It may be a very, very uncertain forecast that we're making for a particular storm, and the potential of it moving outside the cone might be a lot higher than it is typically. So you can't use this error cone because it's also shrinking in size. In 2008, when Ike was threatening the northwestern Gulf, the cone went all the way from the mid-Louisiana coast to north of Tampico, Mexico. But about 8 years later, it shrunk down to this. In another 8-10 years, it may shrink down to this. So the cone is continually shrinking in size as we get better at forecasting each season. That cone shrinks. Every year it shrinks a little bit, and eventually it's going to be a lot smaller. And the effects of the storm are going to be occurring well outside the cone. They already are occurring outside the cone. Let's take a look at the case with Ike. Hurricane force winds all the way to Lake Charles, well outside the cone. So just because you're outside the cone doesn't mean that you're outside of the risk of potential impact from the storm. So you cannot use this error cone as a predictor of whether or not you're going to be impacted by a storm. Now, in something that we've developed in recent years to take the place in the future of this error cone is something called our track guidance, threatened regions from active cyclones, where we take a group of models and their ensemble runs. Ensemble run is an additional run of a model that starts out with a slightly different initialization because we have a lot of uncertainty over what's happening out there in the upper atmosphere across the tropics. And a good deal of uncertainty means that you might have picked the wrong initialization of the model to begin with, and so there might be some error in the forecast. And we take a look at all the models, not just one model, but a conglomeration of over 100 model runs, and we can make a map that shows where the storm is more likely to track based upon a group of models, a consensus better than one individual track here. In the case of Laura, did a very good job when the center of Tropical Storm Laura at the time was over Hispaniola, predicted a landfall near the Texas-Louisiana border, and that's using a group of models, not just one model. For the case of Irma in 2017, this is all the deterministic model runs and the ensemble runs that we see in the background here. We don't show you this map, but we take all of these runs and we calculate the chance of the storm passing near your location, and it comes up with a map like this, which did a very good job in predicting where Irma was going to track. That's the actual track of Irma back in 2017. Very good tool, and we use that as forecasters, and it's available on your Storm Geo web portal for you to take a look at as well. It's very good to use to identify whether the threat is over a larger area, and sometimes it's going to be rather narrow like Irma. Sometimes it's going to be quite wide, indicating much more uncertainty in the forecast track. Future development includes a map like this that includes the probability that you're going to be impacted by a storm-specific wind field over the next 7 days. Number 4, the misuse and misunderstanding of the Saffir-Simpson hurricane wind scale. And I emphasize the word wind there because the Saffir-Simpson wind scale was developed in the late 60s, early 70s by Herb Saffir, a civil engineer, and Bob Simpson, former NHC director, and they wanted to try to estimate at what particular max sustained winds are buildings going to withstand particular damage, buildings and structures. And so it was a wind scale to estimate potential wind damage from those maximum sustained winds. Well, the problem with the scale is that somewhere in the 80s, I believe it was, that a storm surge scale was introduced into the Saffir-Simpson wind scale. And that was never the intention because the a hurricane storm surge is very, very slightly dependent upon the max sustained winds because the max sustained winds could be only over a few square miles or could be over hundreds of square miles. It depends on the size of the wind field. That's what generates a larger storm surge, not necessarily the peak winds that might occur only over a small area. So if you have a plan that says, well, we stay put for category 1 and 2, we evacuate for 3, 4, and 5, I can tell you that In some cases, a Category 1 hurricane can generate a larger storm surge than a Category 5 hurricane, depending upon the size of the wind field. If we look at Ike and Marco, now they weren't occurring at the same time. I superimposed Marco image over the satellite picture here, and we can see Marco very, very tiny, only about 40, 50 miles across. Ike, hundreds of miles across. Ike's hurricane force winds extended over a very, very large area. That's why, as a Category 2, it produced a larger storm surge than the Category 4 Great Galveston Hurricane back in 1900. So size of the wind field is very, very important. We developed a tool to take the place of the Saffir-Simpson hurricane wind scale. It's called our Hurricane Severity Index. We developed this at the end of the 2005 season. It's a 50-point scale. 25 points do take into consideration the projected intensity, but 25 points take into consideration the projected size of the wind field. And that size of the wind field can be used as a predictor of whether or not your location or a location is going to be impacted by storm surge inundation. Take a look at a couple of examples. Two identical on Saffir-Simpson scale. Ivan on the left in 2004, Dennis on the right, hit almost the same areas. The hurricane force winds are indicated in the red shading here. And if you look at the Hurricane Severity Index size component for Dennis it was 20. 20 out of 25 points indicates a very large, for Ivan, 20 out of 25 points for the size component, and for Dennis over here, only 6 size components. Dennis would generate a much smaller storm surge for any area that it impacted than would a large storm like Ivan. So it's very important to know that size component, and that can be incorporated into a hurricane response plan depending upon how high your location is, how susceptible it is to storm surge. A number can be generated that indicates potential inundation. Number 3, the use of proximity trigger. Well, what is a proximity trigger? Proximity trigger means a storm is within X miles of your location, or a storm is, say, entering the Caribbean Sea and you're in the Gulf Coast. If a storm enters the Caribbean Sea, then it's a threat to my location. We assume it's a threat, and you take a particular action. Maybe just initiating a response plan, but that may not need to occur depending upon the forecast. We take a look at Wilma in 2005. It may have been 2 days away from potentially impacting the upper Texas coast, but with Wilma, we were fairly confident that there was a jet stream blowing across the Gulf from southwest to northeast, and that jet stream was going to drive the storm to the northeast across Florida. It wasn't going to be heading toward the upper Texas coast, so there was no threat. Even though it was in 2 days or 1,000 miles proximity from a location, there wasn't any threat. You didn't need to activate your hurricane response plan. And so to take the place of proximity, we developed a tool called our Response Plan Activator. And what that is our hurricane experts take a look at a disturbance, in this case, in the eastern Caribbean Sea. We know it's projected to track to the northwest, and we know that it's likely to impact or threaten at least the islands in the western Caribbean Sea and offshore areas, and also perhaps the northwestern Gulf of Mexico. And because of the threat that we identify, we had sent a notification to our clients that we think there's enough of a risk that you should activate your response plan. Number 2, taking into consideration potential flooding. And we've seen many flooding issues in recent years. Flooding is not a new thing. This is a study we did for just Texas. It doesn't include other locations, but they frequently stall in Texas, particularly during the summertime when the high pressure is stalled to our north and hurricanes occasionally stall over Texas. And we can see that we've had some very heavy rainfall events in the past. The 2 most recent would be Harvey in 2017 and Allison, which wasn't even a tropical depression when it caused a significant rainfall across southeast Texas that Friday night, dumped 35 to 40 inches of rain just overnight. Harvey's rainfall was over a 5-day period. We can compare the 2 rainfall events here. Harvey on the right, the yellow dashed line is the 25 plus rainfall amounts at Harvey. The yellow dashed line for Allison is 25 plus, and you can see only a very tiny area northeast of Houston and northwest of Beaumont for Allison. So much smaller area of heavy rainfall with Allison as with Harvey. Over 15 counties here, or 15 counties with over 25 inches of rainfall from Harvey, widespread flooding. And it wasn't really a surprise that we were going to see flooding with Harvey, because we saw something different. We saw that it was going to stall, and this was a graphic from the National Weather Service, and we were saying the same thing. We could see perhaps 3 feet of rainfall from Harvey because it was forecast to stall down near the lower to middle Texas coast and generate very heavy rainfall. Now, we weren't sure exactly where that heavy rain, or the core of heavier rain, was going to occur. Initially, it looked like it might be closer to the core of Harvey, but it turned out that it was between the Houston-Galveston area and Port Arthur toward the upper Texas coast. But this whole area indicated perhaps up to 30 inches of rainfall. So it wasn't a surprise that some areas received very significant rainfall, it's just difficult to predict exactly what area is going to have the heaviest rainfall when a hurricane is making landfall, or even a tropical depression or a tropical storm is making landfall, because it's not about the intensity. This rainfall is all about the speed of movement of the storm. That's what's very important. And we do know that, and we can forecast that, so we can identify when a very heavy rainfall event is likely with a hurricane or a storm making landfall, and then you can prepare for that to get not just get out of the way of the storm surge, but move sensitive equipment out of range of potential flooding from nearby waterways. Number one, basing your action timeline on a deterministic track forecast. So the deterministic track forecast is just that one forecast. A forecast that's issued either by us or by the Hurricane Center every 6 hours, assuming that that forecast is 100% accurate all the time. We're perfectly confident in the track and that it can't deviate from that track, and that you only take action if a particular wind is projected to impact your location from that one deterministic forecast. That is a mistake. That's the biggest mistake we've encountered. And we can see a typical hurricane response plan starts off with that proximity trigger at phase one, but more importantly, this part of the plan. And I've seen hundreds of plans over the decades that I've worked with these response plans. They always look like this: 120 hours out, 96 hours out. And I ask, what does out mean? And almost no one can tell what out means. How do they determine when out is reached? Without being a hurricane expert, it's really hard to determine when you're within, say, 96 hours of being impacted by a hurricane. What we can do is we can take a look at a timeline here. We can generate a timeline. We can take a look at a projected track. This was Ike in 2008. There were no tropical storm force winds predicted for the upper Texas coast at this time. But we can calculate a worst case arrival time. We can give you a timeline. Say the storm is within 84 hours of affecting or impacting the upper Texas coast, assuming it changes course and tracks in that direction. But you can't just use a worst case arrival time. We have to consider, well, whether it's heading in your general direction, we consider the probability. The probability is based on the projected size of the wind field, and that determines what are the chances of your location being impacted by a storm. We look back at a storm here like Ike, and we generate a probability graphic. We generate numbers here, and you can see that just north of Tampico, 20% chance of being impacted. Just over toward Port Arthur, 20% chance. Certainly a little bit higher right along the track, but all areas in the general path of Ike in this case were at risk. And so just because it's forecast to hit here doesn't mean it can't change track or change directions in the next forecast and threaten the upper Texas coast or even into northeastern Mexico. So you have to take into account not just a potential arrival time, but also whether it's heading in your general direction. That's governed by the probability of wind impact. And we look back over past storms, many past storms. We use the probability of 58 mile per hour winds because that represents the core of a hurricane, of a strong tropical storm or hurricane. That's where most of the damage is going to occur. And it gives you some very good probability values. And we looked at storms that were heading toward a location and eventually hit, and toward a location that eventually veered away. And we've determined that there are specific probabilities that exist. And we can take a look at that graphic a little bit more simply here, and that beyond 48 hours, within 48 hours, the forecast is usually pretty good. We don't have too much forecast error between the arrival time, the forecast, and the worst case arrival time. But we can look at a graphic here showing on the bottom graphic, the worst case arrival time that we calculate of tropical storm winds and the probability of 58 mile per hour winds on the left axis here. And in 3, 4, and 5 days before potential impact, before the potential arrival time, specific values exist, and these values can be incorporated into a response plan to produce objective guidance. Let's take a look at how this might be done for, let's say, this 96-hour point here. 96 hours, their range is somewhere between 8 and 23%, and it depends on the projected size of the wind field generally. And this determines whether the storm is heading in your general direction, and it could be at your location within 96 hours. And so we take that 96 hours out trigger and we make it objective. Worst case, the storm could arrive within 96 hours, and it's very important, both must be met. The probability of wind impact must be, in this case we chose 15%. Could be lower, could be higher, depending upon your level of risk at any particular step along your hurricane response plan. But now we have an objective timeline, and we can incorporate that throughout the plan, starting with that response plan activator to trigger the plan, and then using objective guidance all along the track, and within 48 hours switching to the forecasted time of arrival of the wind field, and look at whether or not the 58 mile per hour plus winds are going to impact your location to identify whether you're going to see a grazing event of a couple of hours of 40 mile per hour winds, or whether you're likely to pass in or near the core of the storm. So this can be used as objective guidance in a hurricane response plan. And with those tools, we developed what's called a trigger report. At the top, we show the current conditions. Currently, you're at phase C. We estimate you should be at phase C's response plan, and we can calculate that next phase, phase D, is going to occur in 48 hours. Some graphics are included, the tools that we're using to arrive at whether or not a trigger has been met. And at the very bottom is where our objective tools are incorporated with your hurricane response plan. Not only can we calculate what phase of your response plan you should be at currently based upon the forecast arrival time. Here, this is 71 hours before forecasted arrival time, within that 72-hour time frame now. So yes, that trigger has been activated. We can calculate when the triggers are going to be reached in the future, so you have a good idea when you're going to have to activate each phase of your response plan going forward. Objective guidance is always going to be much better to use than subjective guidance, and this has become very important for most of our clients now. So that's a look at the top 5 problems that we've identified with most hurricane response plans. Thank you for viewing. Have a safe hurricane season.